Look at that dot. That dot right there is the sun. Not some artistic representation, not a diagram. That is the actual sun, photographed from a distance of 6 billion kilometers by the Voyager 1 spacecraft on February 14, 1990. Carl Sagan called it a pale blue dot. It is, in every measurable sense, everything you have ever known, loved, feared, or dreamed of. Now here's what I need you to understand before we go any further. Voyager 1, launched in 1977, is the fastest, farthest traveling object humanity has ever built. It took 35 years to reach that distance. 35 years of continuous travel through the void, and Voyager 1 is moving at 17 kilometers per second. That is 61,000 kilometers per hour, faster than anything you can possibly imagine. Here's the mind-blown moment number 1. At that speed, it would take Voyager 1 approximately 73,000 years to reach the nearest star beyond our Sun, Proxima Centauri, which sits just 424 light-years away. 73,000 years. Not 73 years, not 730 years. 73,000 years. And that's the closest star. There are an estimated 200 to 400 billion stars in our Milky Way galaxy alone. There are more than 2 trillion galaxies in the observable universe, and we cannot reach even one of them. Not with any technology we have. Not with any technology we can currently conceive of. And by the time you finish this video, you will understand exactly why, and why the universe, at the deepest physical level, seems almost deliberately engineered to keep us trapped right here. Before we dive in, if you're new here, hit that subscribe button right now, because what we're about to cover spans physics, biology, mathematics, and philosophy, and every section is going to leave you more stunned than the last. Seriously, bookmark this one and smash that like button. Not for the algorithm, although yes, that helps, but because this video took months of research to build, and if it blows your mind even half as much as it blew mine, you'll want other people to find it. Now, I want to know something. Drop it in the comments right now. What country are you watching from, and what time is it there? Because right now, as you watch this, there are people scattered across this tiny pale blue dot. In Tokyo, in Lagos, in Mumbai, in Sao Paulo, in Oslo, all staring at their screens, all confronting the same impossible truth, that we are, all of us, marooned. Tell me where you are. I'll be reading comments throughout. Here's the roadmap of what we're going to cover over the next 3.5 hours. And yes, every single section is going to be worth your time. We'll start with the raw mathematics of distance. Why the numbers are so obscene they don't feel real. Then we'll look at what happens to the human body in deep space. And spoiler, almost everything in the universe is trying to kill you. Then we'll attack the energy problem, because the amount of energy needed to send even a small probe to another star is genuinely incomprehensible. Then we'll get into time, both the physics of it and the human tragedy of it. Then we'll explore the proposed solutions, warp drives, wormholes, generation ships, and why, one by one, reality refuses to cooperate. And then, in the final section, we'll confront what all of this actually means. For you, for humanity, for the question of whether we are alone. Ready? Let's go. What if I told you that the biggest obstacle to interstellar travel isn't technology? It isn't fuel, it isn't radiation, it isn't politics or money or will. It's the universe itself. The sheer, unthinkable, almost offensive scale of the cosmos. Let me try to make this real for you, because the numbers alone don't work. The human brain did not evolve to feel the difference between 1 million and 1 billion, let alone the difference between a light year and a megaparsec. So we have to cheat, we have to use analogies. Think of it like this. If the sun were the size of a basketball, a standard NBA basketball sitting on a table in front of you, then Earth would be a small pea, about 26 meters away. The moon would be a grain of sand, 7 centimeters from the pea. Still with me? Good. Now let's find our nearest stellar neighbor, Proxima Centauri, on this same scale. That basketball sun is on your table. Proxima Centauri, on the same scale, would be another basketball sitting approximately 7,200 kilometers away. That's roughly the distance from New York to London. Let that land. One solar system is the size of a small room. The distance to the nearest star, on the same scale, is the distance between two continents. And that's the nearest star. The center of our galaxy is the equivalent of 390 million kilometers away on this scale, roughly 2.5 times the actual distance from Earth to the Sun. The edge of the observable universe? Don't even start. Now let's talk about light years, because I think most people misunderstand what a light year actually is. And once you truly understand it, you'll never look at the night sky the same way again. A light year is not a unit of time. It's a unit of distance. Specifically, the distance light travels in 1 year, and light travels at approximately 299,792 kilometers per second. In 1 second, light travels a distance equal to 7.5 laps around the entire Earth. In 1 minute, it reaches the Moon. In 8 minutes, it crosses from Earth to the Sun. In 1 year, it travels approximately 9.46 trillion kilometers. Mind-blown moment number 2. When you look at Proxima Centauri, which is visible to the naked eye in the southern hemisphere, you are not seeing what it looks like right now. You are seeing light that left that star 424 years ago. You are literally looking into the past. But it gets weirder. The Andromeda Galaxy, the nearest large galaxy to our own, visible on a clear dark night as a faint smudge, is 2.537 million light-years away. The light hitting your retina when you look at Andromeda left that galaxy 2.5 million years ago. Homo sapiens as a species is only about 300,000 years old. You are seeing a galaxy as it was before humans existed. The most distant objects we can observe, some of the earliest galaxies in the universe, are over 13 billion light-years away. We are seeing them as they were 13 billion years ago, when the universe itself was less than 1 billion years old. Those galaxies almost certainly look nothing like that anymore. Some may not even exist. We are not observing the universe. We are observing the ghost of the universe, a cosmic time capsule that takes billions of years to deliver its message. Now here's where the physics gets genuinely brutal. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would rewrite our understanding of reality. His name was Albert Einstein, and his special theory of relativity contained a conclusion so counterintuitive that physicists argued about it for decades. Nothing with mass can travel at or faster than the speed of light. It is not a technological limitation. It is not an engineering challenge. It is a fundamental, absolute law of the universe. Here's why. As an object with mass accelerates, as it moves faster, something bizarre happens to its mass. Relativistic mass increases. The faster you go, the more mass you appear to have. At 10% the speed of light, you have about 0.5% more mass than at rest. Fine. At 90% the speed of light, you have about 2.3 times your rest mass. Okay, that's weird. At 99% the speed of light, you have about 7 times your rest mass. At 99.9%, about 22 times. At 99.999999%, about 707 times. Think of it like this. Imagine trying to push a boulder uphill. The hill gets steeper the faster you try to push it. At some point, the hill becomes vertical, a wall. No matter how much force you apply, you cannot go further. That wall is the speed of light. To reach the speed of light itself, you would need infinite energy. Literally, mathematically infinite. Because at exactly c, the speed of light, your relativistic mass, becomes infinite. And F equals ma, force equals mass, times acceleration. Infinite mass requires infinite force. The universe literally cannot provide infinite energy. Therefore, no object with mass can reach the speed of light. Full stop. Einstein proved this mathematically, and every single experiment ever conducted, including the particle accelerators at CERN, smashing protons at 99.999991% of the speed of light, has confirmed it absolutely. So what can we achieve? Let's look at the actual numbers. Our fastest spacecraft ever, the Parker Solar Probe, launched in 2018, which uses the Sun's gravity to accelerate, has reached speeds of about 163 kilometers per second. That's 0.05% of the speed of light. At that speed, to reach Proxima Centauri, 4.24 light-years away, would take approximately 8,500 years. Even if we could somehow reach 10% of the speed of light, which would require energy output so enormous they are almost incomprehensible, it would still take 42 years one way to reach Proxima Centauri. Anyone who left would arrive as an old person. Their grandchildren might still be alive back on Earth. At 50% of the speed of light, purely theoretical, far beyond anything we can currently achieve, the trip takes 8.5 years. Still more than a decade. And remember, Proxima Centauri is just the starting point, the first step. Beyond it, the next nearest star systems are 6, 8, 11 light-years away. The nearest stars with potentially habitable planets, based on current evidence, are 12 to 40 light-years distant. The galactic center is 26,000 light-years away. Here's the retention hook to carry you forward. We've established the scale problem, but scale is just the beginning. What we haven't talked about yet is what space actually does to the human body. And that's where this gets truly disturbing. Stay with me. In 1950, physicist Enrico Fermi was walking to lunch at Los Alamos National Laboratory with colleagues when he made an offhand remark that became one of the most famous questions in science. But where is everybody? This is now called the Fermi paradox. If the universe is this vast, this old, 13.8 billion years, and if stars and planets are this common, astronomers estimate there are more planets in our galaxy than there are grains of sand on all of Earth's beaches. Then why haven't we detected any signs of intelligent life beyond Earth? One possibility, and a chilling one, is that the distances are so enormous and the energy requirements so extreme that interstellar travel and communication are simply impossible for any civilization, no matter how advanced. That the cosmos is full of islands of intelligence, each one marooned in its own cosmic sea, unable to reach any shore but its own. That would mean we are not alone. But we might as well be. Let's keep going. Because the distance problem? That's just the appetizer. What if I told you that the human body, this magnificently complex machine that has spent 4 billion years evolving, is almost perfectly engineered for exactly one environment, the surface of planet Earth. Step off that surface and everything changes. Space is not empty, space is not peaceful. Space is a brutal, relentless environment that attacks the human body from every conceivable direction simultaneously. Let's go through the assault, one by one. First, radiation. Earth has two shields protecting you right now, the atmosphere and the magnetosphere. The atmosphere absorbs most of the dangerous radiation from the sun. The magnetosphere, generated by Earth's iron core, deflects cosmic rays and solar wind particles that would otherwise shred your DNA. In deep space beyond Earth's protective cocoon, you have neither. NASA's data from the Mars Science Laboratory, which spent 8.5 months in transit to Mars, measured radiation levels of approximately 1.8 millisieverts per day during the cruise phase. The annual limit for radiation workers on Earth is 50 millisieverts per year. Astronauts in transit to Mars are absorbing the equivalent of about 3 years of allowable radiation exposure every 2 months. Mind-blown moment number 3. A round trip to Mars, not even leaving our solar system, would expose astronauts to radiation doses that significantly elevate lifetime cancer risk. The data from astronaut Scott Kelly's year aboard the ISS, published in Science in 2019, showed measurable DNA damage, cognitive changes, and genetic expression differences compared to his identical twin brother on the ground. But solar radiation is actually the lesser concern. The real terror is cosmic rays. Cosmic rays are high-energy particles, mostly protons, some heavier nuclei, accelerated to near light speed by supernovae, neutron stars, and black holes across the galaxy. They rain down on everything in space constantly, from all directions, and nothing we currently know how to build stops them. When a high-energy cosmic ray passes through your body, it doesn't just damage one cell. It creates a cascade, a shower of secondary particles that can damage or destroy multiple cells along its path. In your brain, this can create what astronauts sometimes report as light flashes, visual events caused by cosmic rays passing through the optic nerve or directly through the visual cortex. Astronaut Don Pettit, who has spent time aboard the ISS, describes seeing flashes of light with his eyes closed. cosmic rays piercing his skull and triggering his visual system directly. This happens regularly in space. Now imagine that, not for a few months aboard the ISS, which still benefits from partial protection from Earth's magnetic field, but for years, decades, in deep space, with no protection whatsoever. Dr. Charles Limmerly at the University of California, Irvine, has been studying the effects of cosmic ray-like radiation on animal brains. His research, published in 2017 in Scientific Reports, showed that exposure to iron and oxygen ions, similar to cosmic rays, caused cognitive impairment, anxiety behavior, and synaptic damage in mice. He concluded that astronauts on long deep space missions would likely suffer significant and potentially permanent neurological damage. Think of it like this. Imagine your brain is a city. Cosmic rays are not ordinary weather, they are not even a storm. They are random, unpredictable missile strikes, hitting infrastructure, destroying buildings, cutting communication lines, and there's nowhere to shelter. Radiation isn't the only problem. Microgravity, the condition of apparent weightlessness in space, does devastating things to the body over time. In microgravity, your bones don't need to support your weight, so they don't. Bone density decreases at a rate of about 1 to 2% per month in space. Compare that to osteoporosis on Earth, which causes about 1% bone loss per year. Astronauts who spend 6 months on the ISS return with significantly reduced bone density in their spines and hips. Some never fully recover. Muscles atrophy too, particularly the postural muscles, the ones your body uses to hold itself upright against gravity. Even with 2 hours of mandatory exercise every day aboard the ISS, astronauts return to Earth physically weakened, often unable to walk unassisted for the first days back. Your cardiovascular system changes. On Earth, your heart works against gravity to pump blood upward to your brain. In microgravity, blood shifts toward your head, causing the puffy face bird legs phenomenon observed in astronauts. Your heart, facing less resistance, becomes smaller and weaker. Your circulatory system literally remodels itself. Your vision changes. The shift of bodily fluids toward the head increases intracranial pressure, which pushes on the back of the eyeball, distorting its shape and changing how light focuses. NASA data shows that nearly 60% of astronauts who spend extended time in space develop measurable changes to their eyesight, and in some cases, the changes are permanent. And then there's the mind. Astronauts who see Earth from space often report a profound perceptual shift, a sense of awe, of interconnectedness, of the arbitrary nature of borders and conflict. It's been called the overview effect, a term coined by author Frank White in 1987. It's described as one of the most moving experiences a human being can have. But interstellar travel would be the anti-overview effect. There would be no blue marble to gaze at, no sun visible as anything other than a fading point of light among billions of others, no Earth, no home, nothing familiar. Just an endless dark in every direction, and the knowledge that you and everyone on your ship will die long before you reach your destination. NASA-funded studies of psychological isolation, including the HIC's mission in Hawaii that simulated Mars missions, found that even in simulated isolation, on a planet with communication back to Earth, crew members experienced conflict, depression, communication breakdowns, and diminished cognitive performance. Think of it like this. Imagine being in a submarine, a very small one, with the same 5 to 10 people, with no way to leave, for not months, but years or decades. No new faces, no new environments, no contact with anyone outside. The psychological toll would be catastrophic, and we have no way to prevent it. The human body evolved on Earth, for Earth. It is not a vehicle designed for interstellar travel. It is a finely tuned instrument built for a very specific, very narrow band of conditions. The universe, by contrast, is almost entirely composed of conditions that are lethal to us. And we haven't even talked about the energy problem yet, which is where things go from disturbing to mathematically terrifying. Here's where I need you to pay close attention, because this section is going to reframe everything you thought you knew about rockets and space travel. In 1903, a Russian schoolteacher named Konstantin Tsiolkovsky derived what is now called the Tsiolkovsky rocket equation, It is, without question, the most consequential and most discouraging equation in all of aerospace engineering. The equation says the change in velocity of a rocket equals the effective exhaust velocity multiplied by the natural log of the ratio of initial mass to final mass. What does that mean in plain language? It means that to go faster you need more fuel, but more fuel makes you heavier. And being heavier means you need even more fuel to accelerate that extra weight, which makes you heavier still, which means more fuel, which means more weight. Think of it like this. Imagine trying to throw a ball as far as possible. Now imagine the ball is tied to a rope attached to a boulder, and the boulder is tied to an even bigger boulder. Every effort to throw it just adds more weight. That's the rocket equation. Every increment of velocity requires exponentially more fuel. Let's run the numbers for interstellar travel. Let's say we want to send a small spacecraft, let's be generous, 1,000 kilograms, about the weight of a car, to Proxima Centauri. And let's say we want it to get there in a reasonable time, 100 years. Not a quick trip, but something within the span of a human civilization's planning horizon. To travel 4.24 light years in 100 years, you need to average about 4.24% of the speed of light. Let's round to about 5% of c, and you need to decelerate at the other end, so you actually need to accelerate to 5% c, and then decelerate from 5% c. Using the most efficient propulsion system currently in development, nuclear pulse propulsion, based on Project Orion, which was actually seriously studied by the US government in the 1950s and 60s, the mass ratio required, fuel to payload, would be approximately 1,000 to 1. Meaning for every 1 kilogram of spacecraft, you need about 1,000 kilograms of fuel. So our 1,000 kilogram spacecraft needs 1,000 kilograms of fuel, 1 million kilograms. That's 1,000 metric tons of fuel to move a car-sized spacecraft. But wait, we need fuel to accelerate the fuel. The rocket equation strikes back. Mind-blown moment number 4. When you account for the full rocket equation, where you need fuel to carry your fuel, the actual mass of fuel required to send a 1,000 kilogram spacecraft to Proxima Centauri at 5%, the speed of light using nuclear propulsion becomes approximately the mass of a small mountain. And that's for a spacecraft the size of a car. For context, the entire Saturn V rocket that sent humans to the moon, the largest, most powerful rocket ever successfully launched, weighed about 2,950 metric tons fully fueled. It delivered 45 metric tons to the moon. The fuel required for our interstellar mission dwarfs every rocket ever built combined, by orders of magnitude. But wait, I hear you saying, what about antimatter? That's supposed to be the ultimate fuel. Yes, antimatter is the most energy-dense substance we know of. When matter and antimatter meet, they annihilate each other with 100% efficiency, converting all their mass directly to energy via Einstein's EMC2. Nothing else comes close. Chemical fuel converts roughly 1 part in 10 billion of its mass to energy. Nuclear fission converts about 0.1% of mass to energy. Antimatter converts 100%. An antimatter rocket, in theory, could reach significant fractions of the speed of light. So, solved. Problem over? Not even slightly. The current world record for antimatter production. Physicists at CERN's anti-proton decelerator have successfully created and trapped anti-hydrogen atoms. As of recent reports, they've trapped up to a few hundred anti-hydrogen atoms at a time. To fuel an antimatter rocket for an interstellar mission, you would need approximately 1,000 metric tons of antimatter. CERN currently produces about 10 nanograms of antiprotons per year. That is 10 billionths of a gram. At that production rate, it would take approximately 100 billion years to produce the antimatter needed. That's about 7 times the current age of the universe. Additionally, there is currently no way to store antimatter in large quantities without it annihilating with ordinary matter containers. And the cost of producing antimatter at CERN is estimated at about $62.5 trillion per gram. Think of it like this. Antimatter is like a perfect fuel that exists only in laboratory amounts measured in billionths of a gram. Asking to fuel a starship with it today is like asking to fuel a transcontinental flight with fuel measured 1 molecule at a time. Let's zoom out and look at this from a civilizational perspective. This concept was formalized by Soviet astronomer Nikolai Kardashev in 1964, the Kardashev scale, which classifies civilizations by their energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10^16 watts. A Type 2 civilization harnesses the full energy output of its star. For our Sun, that's about 3.8 x 10^26 watts. A Type 3 civilization harnesses the energy of its entire galaxy. Humanity is currently classified as approximately Type 0.73 on the Kardashev scale. We are not even a Type 1 civilization. We have not yet managed to harness all the energy available on our own planet. Most serious analyses of interstellar propulsion systems suggest that a Type 2 civilization, one that can harness the entire output of its star, would be required to send even a small mission to another star system within a reasonable time frame. We are nowhere near that, and the upgrade path from where we are now to Type 2 civilization involves challenges: energy storage, political cooperation, climate, resource management, that dwarf any rocket engineering problem. Stay with me, because now I want to talk about something that might be even stranger than energy: the way time itself becomes an enemy on interstellar journeys. Here's a question. If you could somehow build a ship that travels at 99% the speed of light, and you sent it to a star 100 light-years away, how long would the journey take? You might say, well, at 99% of C, it would take just over 100 years. And you'd be right, from the perspective of someone watching from Earth. But here's what Einstein's special relativity actually says. From the perspective of the traveler aboard the ship, something entirely different happens. Time slows down. Not metaphorically, not psychologically, literally, physically, measurably. The faster you move, the slower time passes for you relative to stationary observers. This is called time dilation, and it is one of the most thoroughly experimentally verified phenomena in all of science. In 1971, physicists Joseph Haefel and Richard Keating put atomic clocks on commercial airplanes flying around the world and compared them to identical clocks that stayed on the ground. The airborne clocks ran slower, exactly as Einstein predicted. GPS satellites have to account for both special and general relativistic time dilation in their programming, or they would accumulate positioning errors of kilometers per day. Mind-blown moment number 5. At 99% the speed of light, time aboard the ship passes about 7 times slower than on Earth. At 99.9%, about 22 times slower. At 99.9999%, about 224 times slower. In theory, a crew traveling at very high relativistic speeds could experience only years of subjective time while centuries pass back on Earth. This leads to what's called the twin paradox, one of the most emotionally devastating thought experiments in physics. Imagine twins. One stays on Earth, one boards a relativistic spacecraft headed for a distant star. The traveler experiences, say, 10 years of subjective time. When they return to Earth, their twin has aged 100 years, or has already died, and their grandchildren's grandchildren are old. The traveler returns to a world that has moved on without them. Everyone they knew is gone. Everything they loved is changed beyond recognition. Interstellar travel, even if it were possible, would be a one-way ticket, not just in terms of distance, but in terms of time. You would be a temporal exile, displaced not just across space, but across history. Think of it like this. Imagine falling asleep and waking up 200 years later. Your house is gone. Your city is gone. Your language has changed. Your culture is unrecognizable. Your family has been dust for a century. Time dilation makes interstellar travel feel less like an adventure and more like a kind of death. Even if we could send people, there's another time-related problem: communication. Radio waves, our fastest method of communication, travel at the speed of light, which means any message sent from a ship at Proxima Centauri takes 4.24 years to reach Earth, and any response takes another 4.24 years. Total round-trip communication time, 8.5 years. You can imagine the practical implications. Mission control couldn't give real-time guidance. Every crisis on the ship would have to be resolved by the crew alone, with no possibility of consultation. Every decision made would be answered, if at all, years after the fact. For more distant destinations, the communication delay becomes generational. A mission to the galactic center would have a communication lag of 52,000 years each way. Any civilization that tried to maintain contact with a colony at that distance would be speaking across an interval longer than the entire recorded history of human civilization, multiplied by 5. And this brings up a point that historians and futurists often raise. Civilizations are not stable over the timescales required for interstellar travel. The oldest continuously existing civilization on Earth, depending on how you count, is arguably Chinese civilization, at roughly 3,500 years. The Roman Empire lasted about 500 years in the West. The United States is less than 250 years old. Ancient Egypt, one of the most durable civilizations ever, lasted about 3,000 years, but it changed profoundly across that time. Now consider, a generation ship traveling at 0.1% of the speed of light to Proxima Centauri would take roughly 4,200 years. That's longer than recorded human history. The people who arrive would be completely unrecognizable culturally, linguistically, and quite possibly biologically from the people who departed. The ship that left Earth speaking English and following 21st century social norms would arrive with descendants speaking a language no one on Earth would recognize, following customs that would seem alien to the civilization that launched them. Who governs that ship for 4,200 years? What happens to democracy or any political system when the people making decisions are thousands of years removed from the people who originally designed those systems? What happens to purpose, to mission, when generation after generation grows up knowing nothing but the ship? These aren't just philosophical questions, they're engineering constraints, and so far we have no good answers to any of them. By now you've heard the phrase empty space so many times it's become cliché. Space is the void, the vacuum, the emptiness between stars. Here's the thing, space is not empty, not even close. Between stars there's the interstellar medium, a diffuse mix of gas, dust, and charged particles that permeates the galaxy. The density is incredibly low by everyday standards, approximately 1 atom per cubic centimeter in our local neighborhood. But when you're traveling at relativistic speeds, those atoms become a serious hazard. At 10% the speed of light, a single hydrogen atom hits your spacecraft with the energy of a particle in a nuclear accelerator. At 50% the speed of light, those impacts carry energy equivalent to cosmic ray bombardment. The interstellar medium, which at low speeds is essentially nothing, becomes, at high speeds, a constant, relentless barrage of radiation and particle damage. Think of it like this. Imagine driving a car at 5 mph through rain. The raindrops feel light on the windshield. Now imagine driving at 1,000 mph through that same rain. The drops become bullets. The interstellar medium is the rain, and a relativistic spacecraft is the car driving at extreme speed. But it gets worse than atoms. The interstellar medium also contains dust grains, tiny particles ranging from molecules to roughly 1 micrometer in size, and occasionally larger objects. At 10% of the speed of light, a dust grain the size of a bacterium, about 1 microgram in mass, hits with the kinetic energy of a bullet. A grain the size of a grain of sand, about 1 milligram, hits with the energy of a large artillery shell. A pebble, perhaps 1 gram, hits with the energy of a small nuclear bomb. Not metaphorically. The kinetic energy calculation is E, 12mv2, and at relativistic speeds, even tiny masses carry enormous energy. In 2016, the Breakthrough Starshot initiative, backed by Stephen Hawking, Mark Zuckerberg, and Russian billionaire Yuri Milner, proposed sending tiny light-sail probes to Proxima Centauri at 20% the speed of light, pushed by a powerful laser array. One of the most serious engineering challenges they identified, protecting the probes from dust grain impacts on the journey. At 20% C, even a single microgram dust particle carries enough energy to potentially destroy a small probe. The Starshot team proposed shaping the sails and coating them with special materials, but there's no proven solution. For a crewed ship, the shielding requirements become almost absurdly heavy. Every centimeter of added shielding adds mass. Mass requires more fuel. More fuel requires more shielding. The rocket equation, again, mocking you from the math. Here's something that trip planning diagrams often gloss over. Getting there is only half the problem. You also have to stop. On Earth, braking is relatively easy. You burn fuel to decelerate, or you use atmospheric drag, or you use magnetic brakes. In space, you have none of those options. You need to carry fuel for deceleration as well as acceleration. But here's the cruel twist. The fuel for deceleration has to be carried with you from the start, which means you need fuel to accelerate the deceleration fuel, which means more fuel to accelerate that fuel, which means the rocket equation again. Some proposed solutions involve magnetic scoops that gather interstellar hydrogen to use as fuel. The Bussard ramjet concept, first proposed by physicist Robert Bussard in 1960. In theory, the ship harvests fuel as it travels. In practice, later analysis by physicists including John Anderson and Grant Meaders found that the drag from scooping the sparse interstellar hydrogen would actually slow the ship down more than the harvested fuel would accelerate it. The idea, while elegant, doesn't work. Mind-blown moment number 6. Every proposed solution to interstellar travel runs into what physicists sometimes call the tyranny of the rocket equation. You need fuel to carry fuel to carry fuel. And for every creative workaround, ramjets, light sails, antimatter, reality has a devastating comeback. The most technologically interesting current proposal for interstellar travel is the light sail, a spacecraft with a vast, incredibly thin, reflective sail pushed by photons from a laser or from the sun. Photons have momentum. When they bounce off a reflective surface, they transfer that momentum. No fuel required aboard the ship. The energy comes from the laser source, which stays behind. The Breakthrough Starshot initiative envisions laser arrays producing about 100 gigawatts of power, roughly equivalent to 100 large nuclear power plants, focused on a sail roughly 4 meters across. The sail and its tiny probe would weigh about 1 gram total. At that power level, the probe could theoretically be accelerated to 20% the speed of light. The journey to Proxima Centauri would take about 20 years. A signal back to Earth would take 4 years. This is the most promising near-term proposal for reaching another star. And the problems are extraordinary. Building 100 gigawatts of phase-coherent laser power, pointing that laser with sub-arc-second precision across billions of kilometers, creating a sail 4 meters across from a material that is only a few hundred atoms thick and can survive the laser pulse without vaporizing, surviving the interstellar medium at 20% C, transmitting any useful data back from a 1-gram probe. These are engineering challenges of almost incomprehensible difficulty, but they are at least physically possible, unlike the speed of light barrier or the infinite energy requirement. Breakthrough Starshot is genuinely trying to solve them. But Starshot is sending a gram-scale robot, not a human being, not a civilization, just a tiny probe that might send back a few photos. What we're not close to is sending humans, and that's what we'll dig into next. Let's talk about warp drives, because if you've watched any science fiction, this is probably the solution your brain went to first. In 1994, physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity that described a mathematically valid solution to Einstein's field equations, a warp metric that would allow a spacecraft to effectively travel faster than light without violating special relativity. The trick? The spacecraft doesn't move. Instead, space itself moves. The region of space in front of the ship contracts while the region behind it expands. The ship surfs a wave of space-time. From inside the ship, the occupants would feel nothing unusual. They're in flat space-time. But from outside, the ship appears to have moved faster than light. This is genuinely brilliant. And it's mathematically valid within general relativity, which is saying something. So, solved? Why aren't we building one? Think of it like this. The Alcubierre drive is like finding a perfectly valid mathematical proof that you can tie your shoes without using your hands. The math works, but the physical implementation requires things that may not exist in the universe. The problems with Alcubierre's warp drive are numerous and severe. First, exotic matter. Creating the warp bubble requires negative energy density, energy with a negative value. This is not ordinary vacuum energy. We have no reliable source of negative energy, and we don't know if it exists in the quantities required. Some quantum effects, the Casimir effect, produce tiny amounts of negative energy, but scaling that up to warp drive requirements is not even in the realm of current physics. Second, energy requirements. Original estimates for the energy required to create an Alcubierre warp bubble the size of a spacecraft were on the order of the mass energy equivalent of Jupiter, converted entirely to exotic matter. Subsequent refinements by physicists Harold White and others have reduced the estimate, but the energy requirements remain absurd by any practical measure. Third, causality and control. A ship inside an Alcubierre bubble cannot send signals outside it, including signals to control the bubble. You can't steer the warp drive from inside. You'd need some external system to control the bubble's expansion and contraction, but there's no mechanism for that. Fourth, Hawking radiation and stability. Analysis by physicists Stephen Finazzi, Stefano Liberati, and Carlos Barceló, published in 2009, suggests that Alcubierre bubbles would be inherently unstable. They would fill with high-energy particles and destroy themselves. The warp drive is a beautiful mathematical curiosity. It is not a blueprint for a spacecraft. What about wormholes? Einstein and physicist Nathan Rosen showed in 1935 that general relativity permits solutions called Einstein-Rosen bridges, connections between distant regions of spacetime. In principle, a wormhole could connect 2 points in space that are light years apart, allowing travel between them in a fraction of the time. This is not just science fiction. The mathematics is real. Physicists Kip Thorne, Michael Morris, and Yuri Yurtsever explored traversable wormholes in a serious 1988 paper in Physical Review Letters. The problems are devastating. First, creation. No wormhole has ever been observed. We don't know how they would form or how to create one. The conditions required, extreme curvature of spacetime, likely require gravitational environments near black holes or in the very early universe. Second, stability. Theoretical wormholes collapse almost instantaneously. Keeping one open long enough to traverse requires, again, exotic matter with negative energy density, in quantities so large they're incomprehensible. Third, size. Any naturally occurring wormhole would be predicted to be microscopic, on the order of the Planck length, 10 TRAWS 35 meters. Expanding one to human traversable size requires exotic matter. Again, fourth, radiation. Stephen Hawking's 1992 chronology protection conjecture argues that any wormhole that could be used for faster-than-light travel would immediately be destroyed by quantum effects, specifically feedback loops of virtual particles. The universe, Hawking argued, appears to actively prevent shortcuts through space-time. Okay, forget faster-than-light. Forget warp drives and wormholes. What if we simply accept the long journey and build a ship that can sustain human civilization for thousands of years? This is the generation ship concept, a vessel large enough and self-contained enough that the people who arrive at the destination are the great-great-great-grandchildren of those who departed. The concept has serious literature behind it. The British Interplanetary Society's Project Daedalus study in the 1970s and the Project Icarus follow-up have produced serious engineering analyses of interstellar unmanned probes. Generation ships go even further, designing a self-sustaining habitat for human civilization. The engineering requirements are staggering. A closed-loop life support system that can operate for thousands of years without outside input. Food production, water recycling, air regeneration, all from scratch, all indefinitely. A social structure that can maintain purpose and direction across dozens of generations. Protection from radiation, micrometeorites, and all the other hazards of deep space. And somehow, propulsion that can maintain thrust over centuries. But beyond engineering, there's a deeply troubling ethical dimension. The The people born on a generation ship never chose to be there. They are born into a mission decided by their ancestors. They have no freedom to leave. They exist to serve a purpose they did not consent to. This is not a small philosophical point. It is arguably the central ethical crisis of the generation ship concept, and we have no good answer for it. I want to pause here, about halfway through, and bring this down to earth. Literally. Because I think there's a risk that everything we've discussed so far feels abstract. Distant problems for future generations, for scientists and engineers and politicians to worry about. Physics problems, not human problems. But I want to argue that this is a human problem. Your problem right now. Think about what the impossibility of interstellar travel actually means for the human story. It means that every human experience, every love, every war, every discovery, every piece of music, every painting, every conversation, every meal, every heartbreak, every triumph, has occurred on one tiny, fragile, pale blue dot. One impossibly small point in an unimaginably vast cosmos. There is no backup. There is no second Earth waiting for us if we destroy this one. There is no evacuation route. The distances are too great, the physics too implacable. The window of opportunity for life on a planet like ours, with the right temperature, the right atmosphere, the right chemistry, the right star, is not guaranteed to stay open. This is not a counsel of despair. This is a call to attention, because here's what the physics is telling us. Everything that matters, every person you love, every ecosystem, every culture, every form of life on Earth, exists on the only habitable world we can reach. It is irreplaceable. Treat it accordingly. In 2000, paleontologist Peter Ward and astronomer Joe Kirschvink published Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument that Earth is not a typical planet, and the conditions that allowed complex life to develop here may be extraordinarily rare across the cosmos. Consider what Earth has going for it. A sun of exactly the right size and stability, a location in the galactic habitable zone, far enough from the dangerous galactic center, close enough to have heavy elements formed in stellar generations before ours, a circular orbit that keeps temperature variation manageable, a large moon that stabilizes Earth's axial tilt, preventing wild climate swings, a giant planet, Jupiter, that acts as a gravitational shield, sweeping up or deflecting many asteroids and comets that would otherwise bombard Earth, plate tectonics that recycles carbon dioxide and regulates long-term climate, a protective magnetic field generated by a partially liquid iron core. Remove any one of these factors, and complex life might never have emerged. Remove several and Earth becomes Mars, a dry, cold, atmosphereless rock. We don't know how many planets in the universe have all of these features simultaneously. It might be rare. It might be extraordinarily rare. The physicist and author David Deutsch argues in his book The Beginning of Infinity that knowledge, explanatory knowledge, the kind that humans create, is the most transformative force in the universe. That a universe with knowledge-creating beings in it is fundamentally different from one without them. If that's right, if knowledge and consciousness and the ability to understand and explain the universe are genuinely rare, then what's at stake in the conversation about Earth's future is not just human survival. It's the continuation of the universe's ability to understand itself. When Carl Sagan said, "We are a way for the cosmos to know itself," he wasn't being poetic. He was making a philosophical claim that conscious knowledge-creating beings are something genuinely remarkable in a cosmos that mostly consists of hot plasma, cold rock, and vacuum. And all of that, everything we are, everything we know, everything we might become, exists on this one world, protected by this one thin shell of atmosphere, warmed by this one middle-aged star. Here's the mind-blown moment number 7. The fact that interstellar travel is essentially impossible means that every extinction-level threat we face, asteroid impacts, climate change, pandemics, nuclear war, supervolcano eruptions, cannot be escaped by running to the stars. We have to solve our problems here, because here is all there is. Astronaut Ron Garan, who spent 178 days aboard the International Space Station, described what he saw looking back at Earth. "I saw the indescribably beautiful, fragile oasis of light," he wrote, Surrounded by the incomprehensible blackness of space, I was filled with an overwhelming sense of gratitude for the opportunity to see the Earth this way, and a sobering contradiction between the beauty of our home and the sad state of affairs on the surface. Edgar Mitchell, who walked on the moon during Apollo 14, described an epiphany on the return journey, a sudden, overwhelming conviction that the universe was in some sense conscious, that everything was connected, that the separation he'd been taught to see between himself and the cosmos was an illusion. He spent the rest of his life trying to understand and describe that experience. The astronauts who see Earth from space consistently return changed. They become more environmentally conscious, more globally minded, less focused on national identity, more aware of the fragility of everything they'd taken for granted. What they're experiencing, I think, is what the physics is trying to tell us. There is no away, there is no escape. There is only here. You don't have to go to space to feel that. The physics is available to anyone who engages with it honestly. Let's get into biology now, because physics and engineering aren't the only obstacles. Our own bodies, the most sophisticated self-maintaining systems we know of, are profoundly unsuited for interstellar travel. Life on Earth began approximately 3.8 billion years ago in the oceans, protected by kilometers of water from radiation and temperature extremes. The earliest cellular life evolved in a world of abundant water, specific chemistry, regulated temperature, and gravity. Every organism that has ever lived on Earth, from the first prokaryote to a blue whale to you, evolved in that context. Gravity is so fundamental to Earth life that we literally didn't know what its absence would do to us until we started going to space. Bones form in response to gravitational stress. The cardiovascular system evolved to pump blood upward against gravity. The vestibular system, your inner ear, evolved to tell up from down using gravity as reference. In microgravity, all of that goes wrong in ways we're still discovering. Here's something that doesn't get enough attention in discussions of space travel: the microbiome. Your body contains approximately 38 trillion bacterial cells, roughly equal to your own cellular count. These bacteria are not passengers. They are essential components of your physiology, regulating digestion, immune function, hormone production, neurological function, even mood and cognition. In space, the microbiome changes. Studies of astronauts aboard the ISS have found shifts in microbial populations. Some beneficial bacteria decrease, some potentially harmful ones increase. The immune system, without the constant low-level challenges it faces on Earth, also changes, becoming dysregulated in ways that researchers are still working to understand. On a multi-generational voyage, the microbiome of the crew would evolve independently, disconnected from Earth's ecosystems, adapting to the closed environment of the ship. After dozens of generations, the microbiome of the ship's inhabitants might be substantially different from Earth's, and with it aspects of their physiology. Then there's genetic drift. In a small isolated population, as a generation ship crew would be, random genetic mutations have larger effects than in large populations. Beneficial traits spread, harmful traits that don't kill before reproduction can accumulate. The descendants who arrive at the destination might be genetically distinguishable from the people who left, not through deliberate genetic engineering, but through the ordinary mechanics of evolution operating on a small, isolated group. Think of it like this: island populations on Earth, animals isolated on islands after geological separation, often evolve distinctive characteristics within surprisingly few generations. The Galapagos finches that Darwin studied were isolated from mainland South America for perhaps 1 million years. But even on shorter timescales, island populations show measurable genetic divergence. A generation ship is an island in space. Speaking of genetics, a sustainable human population requires genetic diversity. Biologists estimate that the minimum viable population, the smallest group that can maintain genetic health over many generations, is somewhere between 500 and 1,000 individuals for long-term survival without problematic levels of inbreeding. Some analyses of generation ships suggest you'd need 160 individuals if the mission allows careful reproductive planning, essentially a eugenic program that assigns who can reproduce with whom to maximize genetic diversity. Others estimate the number is much higher, perhaps 10,000 or more, if you want truly robust genetic health over thousands of years. A ship carrying 10,000 people for thousands of years isn't just an engineering challenge, it's a civilization. With all the complexity, conflict, and unpredictability that implies, what keeps 10,000 people, and their children and their children's children, focused on a mission goal across millennia? What prevents factions, civil wars, mutinies? What happens when a majority vote to change course, or to stop, or to simply give up? These are not rhetorical questions. They are genuine engineering constraints for which we have no solutions. Dr. Nick Canis, a psychiatrist and NASA advisor who has spent decades studying human behavior in isolated, confined environments, identifies several recurring issues: interpersonal conflict that escalates in confined spaces, displacement of negative feelings onto mission control, a gradual detachment from mission objectives, and severe psychological distress from monotony and loss of autonomy. In 2010-2011, a Russian experiment called Mars 500 simulated a 520-day Mars mission with 6 volunteers confined in a facility in Moscow. The results were sobering. Participants experienced marked sleep disruption, sedentary behavior, and symptoms consistent with depression and disengagement. And this was with full communication with the outside world, something interstellar travelers would not have. Now extrapolate those results to a journey not of 520 days, but of decades, centuries, millennia. The psychological architecture of humanity, our need for novelty, for connection, for meaning, for physical space, for the sense of progress, was not designed for this. Here's your retention hook. We've covered physics, biology, psychology, and engineering. But I've been saving one of the strangest arguments for last. The idea that even if we somehow solved all of these problems, there might be a deeper reason why interstellar colonization doesn't work. A reason from mathematics and game theory that most people have never heard of. That's coming up. Engineers have a concept called single point of failure, a component in a system whose failure alone causes the entire system to fail. Good engineering eliminates single points of failure through redundancy. Critical systems have backups. Backups have backups. On Earth or even on the International Space Station, redundancy is achievable because you can resupply, repair, and in extremis, return. If a component fails on the ISS, a resupply mission can bring a replacement within months. If the situation is truly dire, the crew can evacuate in the Soyuz. On an interstellar mission, none of these safety nets exist. You cannot resupply from Earth. You cannot return in any human-relevant time frame. Any component that fails, life support, power generation, navigation, food production, must either be repaired from existing materials or the mission ends. The probability of a complex system failing increases with time, not linearly, exponentially. The more systems you have, the more components, the more time passes. The higher the probability that something will fail catastrophically. Think of it like this. Imagine flipping a coin. Each flip there's a 50% chance of tails. On any single flip that's fine, but flip it 1,000 times and you are essentially guaranteed to get tails at some point. For a generation ship, tails means catastrophic failure. And the ship is flipping coins continuously for thousands of years. Let's return to the Fermi paradox, because it takes on a new dimension now that we understand the barriers to interstellar travel. In 1998, economist Robin Hanson proposed what he called the Great Filter, the idea that somewhere in the progression from simple chemistry to a galactic civilization, there is at least one filter, a step that almost no evolutionary path crosses. Either the filter is behind us, something in our past was extraordinarily improbable, perhaps the emergence of eukaryotic cells, or sexual reproduction, or multicellular life, or intelligence, in which case we are extremely rare, perhaps unique, and the silence of the cosmos is explained by the rarity of minds. Or the filter is ahead of us, meaning most civilizations that reach our level of technology eventually destroy themselves or fail to escape their home system and join the silence. The barriers we've been discussing, energy requirements, radiation, biological limitations, the rocket equation, the impossibility of warp drives, might collectively constitute the Great Filter. Not nuclear war, not asteroid impacts, not AI, just the sheer, implacable physics of a universe that makes expansion across stellar distances essentially impossible for any biological civilization. Mind-blown moment number 8, the deepest one yet. If the physics of interstellar travel constitutes the great filter, then every intelligent civilization that has ever evolved is trapped on its home world. The universe is full of intelligent islands, each marooned in its own cosmic sea, unable to know the others exist. We are not special. We are not unique. We are typical, a typical prisoner in a universe of prisoners. Some philosophers and physicists take this in a stranger direction. Philosopher Nick Bostrom of Oxford University argues that if it's possible to create realistic simulated universes, and if civilizations tend to create such simulations, then the number of simulated realities will vastly outnumber real ones, and therefore we are probably in a simulation. What's interesting is the intersection with our topic. A simulated universe designed to make interstellar travel impossible is considerably more computationally efficient than one where information needs to exist in genuine detail across trillions of light years. If the cosmos is a simulation, the speed of light barrier and the vast empty distances might be the sim's equivalent of draw distance, regions rendered only in rough outline because no observer will ever reach them. This is admittedly highly speculative, but Elon Musk has publicly stated he believes we're probably in a simulation. Neil deGrasse Tyson puts the probability at 50-50. These are not fringe thinkers. Whether or not the universe is a simulation, the barriers to interstellar travel are real, and they all point to the same conclusion. We are here, we are staying here, and everything we care about exists right here. I want to address the optimists in the audience because I know you're there, and I respect you. But technology improves exponentially, I hear you say. Look at computers, transistors doubling every 18 months since the 1960s. If we project that kind of progress into the future, who knows what we might achieve in 500 years, 1,000 years? This is a fair point, and I don't want to dismiss it entirely. Technology does improve, dramatically. Things that were impossible 100 years ago are routine today. It would be foolish to claim we know the absolute ceiling of human technological achievement. But there's a difference between challenges that yield to engineering, making things smaller, faster, more efficient, and challenges that bump against absolute physical laws. The rocket equation isn't an engineering problem, it's a mathematical truth. The speed of light limit isn't a technological barrier, it's a property of space-time. Relativistic mass increase isn't a physics mistake we'll correct later. It's been measured to extraordinary precision in particle accelerators. Progress in propulsion technology might make interstellar probes feasible. Advances in biology and medicine might extend human lifespan, making longer journeys survivable for a single generation. Breakthroughs in materials science might enable better radiation shielding. These are real possibilities, but none of them touch the fundamental barriers. Infinite energy to reach light speed, the impossibility of stable wormholes, the sheer scale of cosmic distances. Those require not better engineering, but a revolution in our understanding of physics itself. Discoveries that overturn what we currently believe to be the fundamental laws of reality. That could happen. History says it might, but it's not something we can plan around, and the odds, based on current understanding, are not good. Let me be clear. I'm not arguing that reaching other stars is absolutely forever, in every possible future impossible. I'm arguing that it is effectively impossible for biological humans with any technology we can currently conceive of. Unmanned probes are a different story. Breakthrough Starshot's proposal, gram-scale laser-pushed light sails at 20% the speed of light, is physically possible. The engineering is extraordinary, but there are no known physics violations. The project has received funding, has a serious scientific advisory board, and has published peer-reviewed work on its challenges. The proposal calls for a laser array generating about 100 gigawatts, roughly 50 times the generating capacity of the world's largest power station. The sail material would need to be a metamaterial with near-perfect reflectivity to avoid being vaporized by the laser. The probe electronics would need to survive 20 years of interstellar radiation and then transmit data back across 4 light-years with a signal too faint to be detected by current radio telescopes. Each of these challenges is severe, but none violates physics. And with serious funding and talent, comparable to, say, the Apollo program, some of these challenges might be solvable within decades. Think of it like this: breakthrough starshot is like proposing to cross the Atlantic not in a crude ship, but in an unmanned message in a bottle. Impossibly light, pushed by the wind, taking years to arrive, sending back a faint signal when it does. Not a human crossing, not a civilization, but a message. If we're going to talk about crewed missions, even to Mars, let alone further, the concept of suspended animation is worth examining. The idea: dramatically slow the body's metabolism, reduce temperature, essentially pause biological processes, and wake up the crew at the destination. This is not purely science fiction. Therapeutic hypothermia, reducing body temperature to treat certain conditions, is used in medicine today. Some animals hibernate for months. Tardigrades can enter a state called cryptobiosis, essentially shutting down all metabolism, surviving extreme conditions for years and then reviving. SpaceWorks Engineering has received NASA funding to study artificial torpor for space missions, specifically a state of reduced metabolism induced through cooling and medical management. Their concept involves cycling crew through 2-week torpor periods during long transits. The challenge is, no human has ever been successfully placed in long-term induced torpor and revived. The physiological effects of months or years of reduced metabolism on the human body are unknown. Cooling the brain enough to suppress consciousness risks cell death. Muscle atrophy would continue even during torpor. But if these challenges can be solved, and they are biological engineering challenges, not physics barriers, torpor could theoretically make journeys of years more survivable for human crews. Not journeys of thousands of years, but years. Here's where we enter genuinely speculative territory, but it's worth engaging with seriously. Some transhumanist thinkers, including Ray Kurzweil, author of The Singularity is Near, and philosopher Nick Bostrom, argue that the long-term trajectory of intelligence is not biological but digital, that minds, given sufficient understanding of neuroscience and computing, can be uploaded or emulated digitally. If this is possible, a very large if, then interstellar travel becomes a different problem. A digital mind can be transmitted as information at the speed of light. It doesn't need life support, food, water, or radiation shielding. It doesn't age. It doesn't require genetic diversity. A signal carrying the digital patterns of a human mind, assuming mind uploading works, could be transmitted to a receiving station at a distant star, where it would be printed into a robotic body or a reconstructed biological body, and the person would continue their existence there. The journey time would still be limited by the speed of light, for 24 years to Proxima Centauri. But the traveler wouldn't experience any of those years. They would transmit from Earth, and from their subjective experience, instantly arrive at the destination. The problems: we have no idea how consciousness arises from brain activity. We cannot currently map a single neuron's complete connectivity. Uploading: a mind might not preserve consciousness. It might just create a copy. The philosophical questions about identity and continuity are profound and unresolved. And building the receiving infrastructure at a distant star requires that you send something there first. Think of it like this. Mind uploading for interstellar travel is like saying, "I'll solve the immigration problem by faxing people." It sounds clever. The analogy breaks down immediately upon examination, but it points towards something real. If the obstacle is biological fragility, removing the biology removes that obstacle. Another proposal: instead of adults making the journey, send frozen embryos. A ship carrying genetic material, thousands of frozen embryos, requires far less life support than a ship of adults. The embryos are thawed at the destination and raised by robotic systems, or by a small crew of caretakers who remained active. The ethics of this approach are not simple. The people who arrive would have had no say in their existence, their purpose, or their isolation. They would have been deliberately created in an alien environment, raised by machines, with no community or culture to inherit. The psychological consequences are entirely unknown. But from a pure engineering standpoint, An embryo ship is far more feasible than a generation ship or a sleeper ship. The mass of frozen genetic material is trivial, the caretaker crew can be minimal, and the genetic diversity encoded in thousands of embryos could found a healthy civilization. None of these solutions solve the fundamental problem of distance and time. They are adaptations to the problem, ways to send something that is not quite a human civilization across the stars and build something that resembles one at the other end. We're entering the final third of our journey now, and I want to shift registers slightly, from engineering and physics into something more philosophical. Because the question of interstellar travel ultimately leads to a deeper question. What is the place of intelligence in the cosmos? In 1973, physicist Brandon Carter proposed the anthropic principle at a symposium on the 500th anniversary of Copernicus's birth. In its simplest form, it states, the universe must have properties compatible with the existence of observers, because observers are necessary to observe it. This sounds circular, and in a sense it is, but it has a profound implication. The universe appears to be extraordinarily fine-tuned for the existence of complexity and life. The fundamental constants of physics, the strength of gravity, the charge of the electron, the mass of the proton, the cosmological constant, are calibrated to extraordinary precision. Small changes to any of them would produce a universe without stars, without chemistry, without life. Physicist Fred Hoyle, the same Fred Hoyle who coined the term Big Bang as a dismissive term and was then stuck with it, discovered in 1953 that carbon atoms could only form inside stars through a process that required an extraordinarily precise resonance in carbon's energy levels. Without that resonance, without that specific number, carbon doesn't form. Without carbon, organic chemistry doesn't happen. Without organic chemistry, life as we know it doesn't happen. Hoyle, a committed atheist, was shaken enough by this calculation to write, "A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. The dominant scientific response to fine-tuning is the multiverse, the idea that there are an enormous number, perhaps infinite, of universes, each with different physical constants, and we necessarily find ourselves in one that permits our existence. This is not fringe physics. The multiverse is a natural consequence of several serious theoretical frameworks, including string theory, which predicts roughly 10,500 possible universes with different physical laws, and eternal inflation, the idea that our Big Bang is one of countless inflationary events generating pocket universes. The lottery winner fallacy is instructive here. If you win the lottery, you shouldn't be surprised that the winning numbers match your ticket. You'd only be surprised if you lost. The apparent fine-tuning of the universe for our existence might simply be the lottery winner fallacy applied at cosmic scale. We exist, therefore we're in a universe that permits existence. But here's what's interesting about the multiverse in the context of our discussion. It doesn't help with interstellar travel at all. Even if there are infinite universes, we're stuck in this one. And in this one, the physics is what it is. Carl Sagan, in his 1994 book Pale Blue Dot, offered what I think is the most honest reckoning with our place in the cosmos. He described Earth as a mote of dust suspended in a sunbeam, and argued that our smallness in space, our confinement to this tiny world, should produce not despair, but responsibility. That because this world is all we have, it deserves our utmost care, our deepest attention, our most serious protection. The physicist Richard Feynman said something similar in a different context. I would rather have questions that can't be answered than answers that can't be questioned. The fact that we cannot reach other stars is, in a sense, a question we cannot yet answer. We do not know what the long-term future of human technology holds. We do not know whether some breakthrough in fundamental physics might one day reveal pathways we cannot currently see. We should hold that uncertainty with intellectual honesty, but the practical, near-term human civilization scale reality is clear. We are here. We are staying here. What we do here, with what we have here, is all that matters. Here's your mind-blown moment number 9. The impossibility of interstellar travel might be the universe's way of telling us something important, that the journey isn't outward, it's inward. Not across light years of vacuum, but into the complexity, richness, and depth of the one world we actually inhabit. Astronomer Carl Sagan had a phrase I find deeply moving. "The cosmos is within us. We are made of star stuff. We are a way for the cosmos to know itself." Every atom in your body heavier than hydrogen and helium was forged in the core of a star that lived and died before the sun existed. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was synthesized in stellar nucleosynthesis and scattered across space when those stars exploded as supernovae billions of years ago. In a very real sense, you are a star, a collection of stardust that has been organized over billions of years into a form complex enough to look back at the stars and wonder about its origins. The stars are not a destination to be reached. They are a context to be understood. They are our ancestors, our origin story, the forges that produce the atoms of which we are made. We can know them, understand them, trace our lineage to them. We cannot visit them, but perhaps that's enough. Perhaps more than enough. I want to be fair to the optimists, so let's look at what serious scientists are genuinely working on. In 2013, NASA physicist Harold White made headlines by claiming he was testing a scaled-down version of an Alcubierre warp drive, looking for microscopic evidence of space-time distortion. He proposed that a modified version of the original Alcubierre concept, using oscillating fields, might dramatically reduce the exotic energy requirements. The physics community's response ranged from cautious interest to deep skepticism. The consensus is that White's experiments, while interesting, have not produced convincing evidence of space-time distortion. The signals he measured are more likely experimental artifacts than evidence of warp effects. But he continues to work and continues to publish. Then there was the M drive, a proposed reactionless drive that claimed to produce thrust without expelling propellant, supposedly by bouncing microwaves inside a closed cavity. This would violate conservation of momentum, which is one of the most foundational laws of physics. Initial tests, including by NASA's EagleWorks laboratory, seemed to show anomalous thrust. The physics world was briefly electrified. Subsequent, more careful experiments, including a 2021 study published in Physical Review Letters by a German team, found that the apparent thrust disappeared when measurement artifacts were eliminated. The M drive almost certainly doesn't work. Conservation of momentum remains intact. There are genuine frontiers in physics where our understanding is incomplete, and those frontiers occasionally produce surprises relevant to space travel. Dark energy, the mysterious force causing the universe's expansion to accelerate, is one of the most profound unsolved problems in physics. We don't know what it is. Some theoretical models suggest it might be a property of space-time itself. If dark energy is better understood, could we manipulate it? Could space-time be engineered in ways we don't currently conceive? It's genuinely unknown. Quantum entanglement, the phenomenon where two particles appear to affect each other instantaneously across any distance, has been proposed as a possible communication channel. In 1982, physicist Alain Aspect and colleagues confirmed entanglement was real, not an artifact of incomplete theories. In 2022, Aspect, along with John Clauser and Anton Zeilinger, won the Nobel Prize in Physics for this work. However, and this is critical, entanglement cannot transmit information faster than light. It can establish correlations between distant particles, but you cannot control what outcome you measure, so you cannot encode a message in entanglement without also sending a classical signal. Physicists call this the no communication theorem, and it's been proven mathematically. Every attempt to use quantum mechanics to circumvent the speed of light limit has failed, and usually the proof of failure is elegant and illuminating about why the universe is structured the way it is. Let me be concrete about what is realistically achievable in space exploration over the next century, without speculative physics. In the near term, 2030s to 2050s, crewed missions to Mars are genuinely feasible, if extraordinarily challenging. Robotic probes to the outer planets and their moons, Europa, Enceladus, Titan, could search for evidence of life in our own solar system. Advanced telescopes, including successors to the James Webb Space Telescope, could characterize the atmospheres of exoplanets for biosignatures, signs of life at astronomical distance. In the medium term, 2050s to 2100s, fusion power, if achieved, could revolutionize space propulsion. Nuclear thermal and nuclear electric propulsion could dramatically shorten inner solar system transit times. Solar sails could enable fast unmanned probes to the outer solar system and potentially to the Oort cloud. In the long term, beyond 2100, laser-propelled light sails, like Breakthrough Starshot, are plausible for small unmanned probes to nearby stars. The first interstellar missions might transmit back primitive photographic data from another stellar system within the 22nd century. Human interstellar travel? The honest answer is not in any foreseeable future, with any technology currently on the horizon. The barriers are not engineering problems, they are physics. If there is one thing that could genuinely transform this picture, one discovery that would change everything, it would be evidence of traversable wormholes, or the discovery that exotic matter with negative energy density exists in useful quantities, or the discovery of some entirely new physics that reveals shortcuts through space-time. We currently have no reason to suspect exist. The history of science includes moments where foundational assumptions turned out to be wrong. Newton's mechanics seemed complete until Einstein showed they were an approximation. Classical physics seemed complete until quantum mechanics showed that reality at small scales is bizarre beyond imagination. It is possible, I want to be honest about this, that our current understanding of physics is incomplete in ways that would matter for interstellar travel. That some as-yet undiscovered phenomenon changes the picture fundamentally. But possible and likely are different things, and planning for the long-term future of civilization on the basis of hoped-for physics revolutions is not wisdom, it's wishful thinking. The evidence, as it currently stands, says we are here for good. Which brings me to the final section, and the most important one. Here's the question I want to end with. Not can we escape Earth, but what does it mean to be here? Because I think we've been framing this wrong. The narrative of interstellar travel, the dream of reaching the stars, implicitly treats Earth as a launching pad, a way station, something to be left behind. It treats the cosmos as a frontier to be crossed, an expansion to be achieved. But what if the cosmos is telling us something different? What if the physics of the universe, the speed of light limit, the vast distances, the relentless hostility of space to biological life, is not a prison but a frame? A frame in art is what makes a painting meaningful. It defines the edges. It focuses attention. Without a frame, a painting bleeds into the wall and disappears. Earth is our frame. The solar system is our frame. The speed of light is our frame. And within that frame, and this one tiny, extraordinary, teeming, complex, impossible world, there is more beauty, more mystery, more depth, more richness than any civilization could fully explore in any time frame. Think of it like this. A musician constrained to a single octave on the piano doesn't have less music available. Within a single octave, there are 12 notes. From those 12 notes, all of Bach, all of Beethoven, all of Coltrane, all of Taylor Swift. Limitation is not the enemy of creativity. It is often the very source of it. Consider what has happened on this planet, this pale blue dot, in the 4.5 billion years of its existence. From the first replicating molecules in war motion vents to the extraordinary complexity of a eukaryotic cell. From a single-celled organism to a blue whale, a creature 30 meters long whose heart is the size of a small car and whose songs can be heard across ocean basins. From the first nervous systems to the 86 billion neurons of a human brain, each connected to thousands of others, forming a network of complexity that rivals anything else in the known universe. And from that brain, language, mathematics, music, art, philosophy, the scientific method, literature, the ability to build instruments that can detect gravitational waves, ripples in space-time produced by colliding black holes a billion light-years away, the ability to decode the human genome, the ability to understand our own origins. We have created on this small world, in this brief evolutionary moment, things of extraordinary beauty and depth, Shakespeare's sonnets, Bach's Goldberg variations, the Taj Mahal, the Hubble Deep Field Image, the equation EEMC2, the discovery of DNA structure, the Voyager Golden Record, a greeting sent into the void by a species that knew it might never be answered. Physicist Richard Feynman, accepting his Nobel Prize in 1965, described the feeling that drives scientific inquiry: the pleasure of finding things out, not the glory of conquest, not the satisfaction of utility, the simple, profound, irreducible pleasure of understanding. That pleasure is available to you right now, not when we reach the stars, right here, right now, on this world. The chemistry of a bee navigating by polarized light, the way a fertilized egg, guided by nothing but chemistry and physics, reliably assembles itself into a complete human being in 9 months. The fact that prime numbers go on forever, proven by Euclid 2,300 years ago with a proof so elegant it still takes your breath away. The way a piece of music can move you to tears without a single word being spoken. The universe did not have to be this way. It did not have to produce structures of such complexity and such beauty. It did not have to produce minds capable of appreciating them. But it did. And those minds, you, right now, watching this, are the universe's way of looking at itself and finding it beautiful. Mind-blown moment, 10. The fact that you exist, that the atoms of which you are made were forged in a dying star, were scattered across interstellar space, were gathered by gravity into a new solar system, were assembled over billions of years into life, and eventually into a mind complex enough to contemplate its own origin, is the most astonishing fact in the known universe. And it happened here, on this dot. And yet, I don't want to leave you with a fully closed door. Because science is not finished, human understanding is not complete. There was a time when humans thought the Earth was flat, and the sky was a solid dome above our heads. There was a time when we thought the sun moved around the Earth. There was a time when we thought continents were fixed. There was a time when we thought atoms were indivisible. There was a time, less than 200 years ago, when we didn't know that other galaxies existed. In each of those cases, the accepted understanding was not wrong because someone had miscalculated. It was wrong because the conceptual framework itself was incomplete, because there were phenomena and realities that the existing framework couldn't see. The speed of light barrier, as currently understood, comes from general and special relativity. Those theories are extraordinarily well tested, but they are also known to be incomplete. They break down at quantum scales and at the centers of black holes. Quantum mechanics and general relativity are inconsistent with each other, and physicists know it. A theory that reconciles them, a theory of quantum gravity, might change the picture. It might not. The barriers we've discussed might be absolute, or they might be like the flat Earth, the boundary not of reality, but of our current imagination. That question, that genuinely open question, is what physicists spend their lives chasing. And it's what science is for. So where does all of this leave us? It leaves us here, on this extraordinary, improbable, perhaps unique world, in the only moment we will ever inhabit, the present, connected to every other human being alive by the shared fact of our confinement, our common maroonment on this small blue dot. The barriers to interstellar travel are not an insult to human ambition. They are a focusing lens for it. They say, this is your stage, this is where the story happens, everything that matters to you, everything that has ever mattered to anyone, happened here. That deserves your full attention. Physicist Freeman Dyson, who spent his career dreaming about interstellar travel and never stopped believing in its eventual possibility, said something that I think is the perfect note to end on. The more I examine the universe and the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming. Whether or not you agree with that, whether you think the universe is designed or random or simulated or something else entirely, the fact remains that you are here. The cosmos produced you. It produced a mind capable of comprehending, however imperfectly, the scale and structure of the universe it inhabits. It produced an organism that can look at a pale blue dot and recognize its home. That is not nothing, that is in fact everything.